The Sun is a massive sphere of hot plasma and the dominant force in our solar system. In this introduction, I explain that every bit of energy that sustains life on Earth, light, heat, and the energy that drives weather, originates from the Sun's internal nuclear furnace. The study of the Sun helps us understand not just astronomy, but climate, seasons, day-night cycles, and the behavior of stars in general. The Sun is an ordinary G-type star, but it dominates our solar system. 99.8% of all the mass in the solar system is packed into our Sun. It's mostly hydrogen and helium, the two lightest elements. The core is the engine where extreme pressure and temperature enable nuclear fusion. Energy moves outward through the radiative zone, where photons bounce endlessly, and then through the convective zone, where hot plasma rises and cool plasma sinks. The photosphere is the visible surface, while the chromosphere and corona form the Sun's thin, extremely hot outer atmosphere. Each layer behaves differently and contributes to the Sun's behavior as a star. Hydrogen is the Sun's primary fuel. Deep in the core, 4 hydrogen nuclei fuse into one helium nucleus through the proton-proton chain. This process releases enormous energy, because a small amount of mass is lost and converted directly into energy using Einstein's equation E = mc². Make clear that this fusion output, 3.8 times 10 to the 26th watts, is what makes sunlight possible and keeps our planet warm. Sunspots are darker patches on the photosphere, but they only look dark because the surrounding material is even hotter. Sunspots form where strong magnetic fields prevent normal convection, lowering the temperature. They often appear in clusters called active regions and move across the Sun's disk, helping us track the Sun's approximately 27-day rotation period. Sunspots grow, shrink, and migrate over the 11-year solar cycle, giving clues about solar magnetism. Solar flares are explosive releases of energy that occur when magnetic field lines snap and reconnect. Coronal mass ejections are massive clouds of charged particles hurled into space. These events vary with the solar cycle and can affect Earth by disturbing satellites, power systems, and radio communication. Explain that studying these helps predict space weather and protect modern technology. The Sun is Earth's main energy source. Sunlight drives photosynthesis, weather patterns, ocean currents, and the water cycle. The solar wind, streams of charged particles, interacts with Earth's magnetic field to produce auroras, particularly near the poles. Explain that without the Sun, Earth would be a frozen, lifeless world. The Sun is about halfway through its stable lifetime as a main sequence star. In roughly 5 billion years, it will exhaust its core hydrogen, expand into a red giant, and eventually shed its outer layers, leaving behind a dense white dwarf. This long evolutionary journey is typical for stars of the Sun's size, giving insight into the life cycles of many stars in the galaxy. In summary, the Sun is a stable, middle-aged star powered by nuclear fusion, displaying magnetic activity through features like sunspots and solar flares. Studying the Sun helps us understand both life on Earth and the broader behavior of stars across the universe.